I want to welcome you tonight to our 8th annual lecture series. So thanks so much for coming. We have a committee of fine folks who help work on this every year and help us find lectures on campus, and I want to recognize them. We have Don Hobby, Ann Boone, and Kitty Robinson. They're here with us tonight, and I want to thank them publicly for their participation. Also, the Missoula Cable Access Television Station is going to videotape the series for us, and we'll find out exactly when those dates are that they'll be showing those on the cable channel. So I'll share that information with you also. So whenever we're done with the lecture, I'll pass the mic for folks so we can make sure we hear what everyone has to say. Our series this year is called Sun to Seeds, Our World Around Us. And this year we decided we needed to look at the sciences and approach the fine faculty we have that work in that area on campus. So we have a great lineup. I want to mention their names here tonight. Tonight we have Professor Gavon Smith, and I'll speak more about him in a moment. We also have Steve Running. He's going to talk about our changing physical environment next week. 2 weeks from now, Dan Reisenfeld. He's going to talk about the life and death of the sun, and he's an expert on the sun, and he's a very renowned astronomist. Ron Wakimoto is March 7th. He's going to talk about fire and smoke in the world around us. Bill Woosner will talk about water, water everywhere. Will there be a drop to drink? And our last lecturer will be Neva Hassanin, and she's going to talk about sustainable agriculture, the power and promise of local food. Professor Gavon Smith is a professor of chemistry here at the University of Montana. He received his BA degree in environmental biology from the University of Colorado at Boulder in 1973 and his PhD in applied chemistry from the Colorado School of Mines in 1983. He's previously served on the faculties of Colorado School of Mines, Colorado College, and SUNY College at Fredonia in New York. At the University of Montana in Missoula since 1991, Dr. Smith teaches the first half of the introductory chemistry sequence for applied science majors, as well as upper division and graduate courses in analytical and environmental chemistry. Each May, in the guise of gee whiz, and as we would say in the hood, that's gee whiz, short for Gavon the Wizard, he performs feats of chemical magic for hundreds of grad school students around the state. In 2004, he was voted UM's most inspirational teacher by graduating seniors and received an Innovative Excellence in Teaching, Learning, and Technology at the 15th International Conference on Teaching and Learning. Since '92, Gavon has been the chemist for the University of Montana's well-publicized Bee Alert project, and that's BEE. Bee Alert uses honeybees to perform environmental sampling and to sniff out buried landmines and hidden explosive caches. While with the project, he held a visiting science position at the Department of Energy's Oak Ridge National Laboratory. Gavon's other research involves environmental applications of mass spectrometry and artificial neural networks. He helps formulate biodiesel from vegetable oil, follows dispersion of pulp mill odors in mountain valleys, and investigates the chemical nature of respirable particulates from sources such as forest fires and motor vehicles. He participates in environmental and health policy formulation at both the county and the state levels, and he's vice chair of Missoula's City County Board of Health and the board's liaison to the Air Quality Advisory Council. He served as the governor-appointed scientist on the Montana Board of Environmental Review from '95 to 2004. As a member of the Board of Governors for the National Conferences on Undergrad Research from '98 to 2004, he chaired the 14th National NCUR Conference held in 2000 here at UM. And he was recently awarded the program chair role again for the 24th conference. And that's going to be held here in Missoula in April 2010. He currently holds the title of Senior Associate with the National Science Foundation's Center for Science and Civic Engagement. He will also be honored this Friday the 17th as UM's 2006 Faculty Service Award at our Charter Day celebration. It's my pleasure to introduce Professor Gavon Smith.
Thank you, Ken, and members of the committee who picked the talks. I'm always amazed to have so many people come out to listen to a talk about chemistry, because usually you mention chemistry and everybody runs the other direction. If you're at a cocktail party and you want to put a damper on things, just say, oh, I work in chemistry, and everybody says, oh, that's nice, and goes somewhere else. So I thought I would try to stir the pot up a little bit here and open up the series with the thought-provoking question, can science save the world? And over the course of the next 6 weeks, you're going to hear 6 people try to use hortatory lecture skills to convince you that if science can't save the world, it's sure a good partner to have. So I thought we'd start this off by talking about what is science anyway? So this is more philosophic than I usually get. So I think of science as a systematic way to explore how things work. And what we're really doing is trying to get to the point where we can be almost fortune tellers. We want to have at our fingertips the kind of knowledge that has predictive power. So we can recognize the situation and say, oh, I know what's going to happen. It's going to be da-da-da-da. That's what we're looking for. If we don't have any predictive power, then the science doesn't seem to have as much use. And science is just bundled up with the idea of knowledge. In fact, if you look at I'm getting feedback here. If you look at the origin of the word science, it actually comes from the Latin word meaning having knowledge. So that's what we're after. And science actually is a pretty tough field to make your way in if you're not almost a lawyer of a different sort. Science is evidentiary based, and the science community is very reluctant to accept anything unless you can mount a persuasive set of arguments. And in fact, you can even see that in the language that we use. We talk about Newton's first law, Newton's second law. You can see the legal proof, burden of proof right in there in the way we say, we're going to accept this as a law. And of course, we talk about doing trials in the lab, and we have to, unlike attorneys who can't have double jeopardy as far as trying somebody for the same crime twice, we're put thumbs down if we don't do our trials over and over and over again and show they keep working. So it's a pretty demanding community, but I think that's part of why it has a role to play and the reputation it does. So how do we do science? Well, purportedly, we use this thing called the scientific method, where we make observations, have our curiosity piqued. From the observations, we then say, I wonder how that works. So now we start thinking, and we wouldn't want to call it a guess, because that would sound like it's not sophisticated enough. So we say, I'm going to formulate a hypothesis here. Fancy word, euphemism for a guess. And if it's a good hypothesis, it suggests a test that we can run to see how good it is, which is what an experiment is. So we perform the experiment, and as the experiment is being conducted, we make new observations. And then we have to say, my hypothesis wasn't correct. I need to redesign it a little bit. So I thought I would put on my hat here, and we would try the scientific method. This is the way science used to be done. And the wizards would not divulge their secrets because that was their livelihood. But of course, we've just switched the way we do this, and now as long as we charge tuition for the secrets, or at least the price of an admission ticket here, we can still make a living at being a wizard. So I'm going to pour out a couple of potions here. And I always point out that this looks just like measuring out ingredients in the kitchen, that chemistry is is cooking, and we just can't eat all of our recipes when we do them in the lab. Usually in the kitchen we can, but every once in a while we can't even eat those either. So I'm going to pour out a couple of potions here, and we're going to pour them together, and by virtue of the magical power invested in my fingers, I'm going to turn these into ink. So we'll pour them together and say the incantation. When east is east, and west is west, and one flies over the cuckoo's nest. When red is red, and pink is pink, make this water black as ink, and then I'll rub it with my fingers. It turns into ink. No fancy cameras, right? Pure, unadulterated magic. So if you don't know how the chemistry works, it can seem like you have powers that might be worth paying off before they're invested in putting warts on your daughter's face, right? So this is where the scientist gets engaged. Wow, I wonder how Gavon did that. Now there are some people in the audience here who probably know, but try formulating a hypothesis. Anybody want to make a guess? I make wrong hypotheses all the time. Any guesses at all? I usually have to prod quite a bit with my students too. I do this the first day of class to earn my title of Gee Whiz. Well, just head scratch. I thought that was somebody going to make a guess. Anybody want to make a guess? We need a guesser. Be brave. Pardon? Well, it's a chemical reaction, but why does it wait for my magic powers? Heat from the hand. See, there we go. What were you going to say?
Something got oxidized.
Something got oxidized. Well, that's the kind of reaction it is. Heat from the hand. How would we test that? Do it without my hand. See, a good hypothesis. See, I brought a waste jug here, so I can do it again. I had to test it before you all showed up to make sure it was going to turn into ink. It's very embarrassing if your magic doesn't work. That's why chemistry is in the School of Arts and Sciences. There's some up to this. So we'll pour out another set of solutions, potions here. We have to do everything the same except the touch part. We try to control variables in our experiments so that only one thing is changed, so that when we run our test, we're testing exactly what we're hypothesizing is the critical parameter. So here's another set of potions. And I'm going to put it over here, pour them together, and start my incantation. When east is east, and west is west, and one flies over the cuckoo's nest. When red is red, and pink is pink, make this water black as ink, and then I'll shoot my powers. No heat required. Do you have an idea now? Time. See, I can only get away with it one time. This is a reaction where the color change doesn't happen instantly when you pour liquids together. That's kind of unusual. Most of the time, chemical reactions happen pretty fast in water solution. This one doesn't happen to. In fact, it takes about 15 seconds, the way I've put together the solutions tonight, and the temperature that it is here in the lecture hall. So what I was really doing was timing 15 seconds while I talk to you. That's magic, right? To be able to multitask like that. I'm really not as good as it seems. What I really do is if I say my little incantation with dramatic flair and leave time for my fingers to wiggle or whatever, that takes 11 seconds. So I just pour kind of slowly while I count to 4. And so I can count to 4 while I pour a little bit. So we'll try this one last time. So see, isn't this kind of fun? Doesn't matter which order you put them together. Doesn't matter the amounts. We could, but then I'd have to scrub out both flasks because it leaves little black thingies on the sides. And I'm lazy. So let me see, I'll watch the time here. I won't count the first few seconds because I have to watch while I pour so I don't spill it. So we'll pour it together. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. See? So there you go. You know how the science works. You can predict what's going to happen. I knew it was going to turn into ink after a time delay. So that's what science is all about, is having predictable knowledge. If you wanted the recipes, I knew this was going to happen. I won't adjust the fonts. You can see that I've got a little bit of potassium iodate in one of the flasks, and I've got sodium sulfite. There's an oxidation reduction reaction there. And I'm going to eventually turn the iodate into iodine, and it's going to react with ghost poop, that's the technical name for those packing peanuts that are made out of starch instead of styrofoam. They're more environmentally friendly. Turns out that they're easy to get into solution for me, so I use them to make my starch solution. What we'll see is that in chemical reactions, when we study them, if we're going to completely understand them and know how to predict what they're going to do, we have to pay attention to two different factors. The kinetics of the reaction, which is how long it takes. If you're a geologist, or if you're looking at the life of the sun, you got a long time to wait. But chemists, they can get things done in a hurry. And then we also have to look at the energetics of chemical reactions, which is the thermodynamics part, and that tells which way, if we mix chemicals, the reaction is going to go. If we dump stuff together, is it going to react, or is what we're dumping together what was left over after some other reaction? It also tells us how complete the reaction is. So here's a little diagram of what happened with my ink trick. It started out as KiO3. Actually has to go through 6 steps to turn into I2. Those are kind of slow. The last step is when I get to this I3 minus form plus the starch. Turns out that the product is a catalyst. So this is called an autocatalytic reaction. So as soon as you make a little bit of product, it acts as a catalyst and speeds up more reaction, which acts as a catalyst, which speeds up more reaction. That's why it turns in just a blink of an eye. So I think it's kind of a fun one. Professor Field in our department has spent a lot of his career studying these kinds of reactions. Well, that was a kinetic one. You want to see a thermodynamic one? Because it turns out in the real world, a lot of chemistry is either kinetically controlled or thermodynamically controlled. So I brought a thermodynamic one, just if you were interested. Do you think if you said no, you'd get away with not seeing it? Not a chance. So I brought my little balloon over here. This is not a balloon filled with helium. It's a balloon filled with hydrogen. So let's look at what the thermodynamics of this reaction tell us. Just looking here. Seeing how close that screen is. Here's how we would analyze the thermodynamics of this reaction. We would write down the chemical reaction, and then we'd want to show how much ends up in the product form, H2O, which is gaseous water. We would have to put together a quotient. A K is going to be numbers divided by one another. On top we put how much of the products we have, and every time we have more than one molecule, that works as an exponent. And then we'll take the reactants, the ingredients, and put them in the bottom, and again their molecule counts turn into exponents. That's the quotient we'd look at because it tells us how much ends up in product on top versus how much is left over as reactants when we get done. And if this is a big number, it means it's a reaction that likes to happen. Is this a big number? I would say so. There are not many things you will encounter in the physical world that have 10 to the 81st on them. That is just so imaginably huge, I can't even get a grasp on it. A lot of times I talk about Avogadro's number, which is how many atoms or molecules there are in sort of a cup full of material. If you had that many chemistry textbooks, it would stack up from here to the Andromeda Galaxy. which is 2.5 million light years away. And that's only 10 to the 23rd. This is 10 to the 81st. This is a reaction that likes to happen. So maybe, I noticed that Bill Johnston walks in, maybe we need to have a new version of the Boom Crew at the football games. And this one would be appropriate for because of the hydrogen technology we've been talking about doing. The nice thing about this is that unlike the kind of combustion that Ron Wakamoto is going to talk about with the smoke, this is a smokeless kind of fuel. The only thing that we get out of the combustion reaction is water vapor. So that's one of the nice things if we ever get a hydrogen technology, is we won't have noxious gases coming out of the tailpipes of our car. This is actually a little bit more spectacular if it's a little darker. Well, I don't know how these work. There we go. That's all right. At least I can see. Let's see if we can make this reaction happen to see what 10 to the 81st looks like. So I just have to break a couple hydrogen molecules to get it started. Wasn't that fun? Students don't fall asleep in my class. So now you've seen both a kinetic reaction and a thermodynamic reaction. That's what we do in chemistry, is figure out thermodynamics and kinetics. Of course, what we just looked at was a recreation of what happened to the Hindenburg, because they used the hydrogen. It's twice as buoyant as helium. Unfortunately, it's very flammable, and a static spark caused it to catch fire. It was 803 feet long, and I think it took 4 seconds for the flame to propagate from one end to the other. So it was a fast toasting marshmallow. Once it started, there was no going back. So, is science good or is it bad? Well, science is science. It's kind of impartial as far as we humans go. It's going to do what it's going to do, or what Mother Nature or God has set up for it to do. But people can either use it well or abuse it, and it's had both forms of application. And we also are fully aware that if you're in the field of science, that it's not impartial, that the funding of science is a very big issue, and that gets very political. And of course, as a professor here at the university, I'm rewarded more handsomely if I work the politics of science better. And you also run into some pretty big egos and people who want to get famous and want to take credit for stuff. So science itself is impartial, but using it and producing it do have some problems. And sometimes, even though we think we're using it for a noble cause, we don't have a crystal ball to see what all of the ramifications from that are. So, for instance, DDT. You all go, ooh. Well, look at when it was first used. Back in the 1940s, DDT was used to kill off mosquitoes that were behind a malaria epidemic, and it was hailed as a wonder chemical. The 1948 Nobel Prize in medicine and physiology was awarded for the development of DDT, if you can believe that. How would you like to be known today as the person who got the Nobel Prize for DDT? What we didn't appreciate was that it is so chemically inert, it doesn't break down in the environment, it builds up in the fatty tissues of any animals that consume it, and it turned out that when fish-eating birds tried to break it down, it turned into a second compound called DDE that interfered with the depositing of calcium in their shells, and when the birds set on their clutch of eggs to hatch them, the eggs would break. So it's been banned in the US since 1973. So it started out as having a good cause, but we had some unexpected consequences. Or here's another one, CFCs. They were developed by DuPont, and they were used initially to replace some toxic refrigerants. They used to put ammonia or chloromethane or sulfur dioxide in the coils. If you were defrosting the freezer and poked a hole in the refrigerator coils and it had the methyl chloride, it was a fatal accident. So after a series of fatal home accidents like this, they decided to use these CFCs. And the CFCs are so, again, unreactive chemically that they were hailed as a real improvement for electronics workers because they could degrease the sticky stuff on the circuit boards without getting exposed to toxic solvents. The problem was, and we didn't appreciate this until the early 1980s, is that the CFCs are so stable that they stay in the atmosphere until they get up high where the incoming solar radiation can bash them apart, and there they turn into catalysts that chew up the ozone layer. And the ozone layer filters out harmful ultraviolet radiation, and one CFC molecule can destroy up to about 100,000 ozone molecules before it hits a terminating reaction sequence. So again, unexpected consequences. And then there's these scientists that have made it easier to live longer. And just look at what our historic population growth looks like. These are years BC and AD, and boy, it's an exponential curve going up. Here's looking at how long it took to get to 1 billion, and then 2 billion population, 3, 4, 5, 6. So that's kind of ominous there. When we look at what happens to bacteria, they hit a plateau eventually, and I hope that we get control of this before we get to the point where it becomes real contentious. So these are the guys that are responsible for it. These are your most wanted as far as the human population goes. At least in my mind, this is one crew. There's this first guy, that's Edward Jenner. He developed the vaccine against smallpox, which was the first vaccine. How did he notice that? Anybody remember? Cowpox. The milkmaids weren't getting smallpox. Anybody know the Latin word for cow? Vaccine. Ah, see, it's right there in the word. Isn't that kind of fun? Who's this next guy? This is Louis Pasteur. Very good. He's the one who figured out that it's germs that cause diseases. He did that work starting about 1865. It's not very long that we've known that microorganisms cause diseases. Malaria used to be thought to be due to breathing poisonous gases. It's actually Italian words for bad air, malaria. But Pasteur said, nope, there's these little bug guys, and they're causing the problem. How about this last guy? Fleming. Oops. I didn't change his name. This is Sir Alexander Fleming. I give my students one point of extra credit if they find mistakes in my PowerPoints. So if you find any mistakes in my PowerPoints, I'll give you a point of extra credit. You can tell this is new for tonight, so I actually worked a little bit for you guys. So this is Sir Alexander Fleming, who in 1928 found penicillin. He found it by accident, and it actually didn't get very good play when he wrote it up in the technical literature, and it was only later during World War II that it was worked out and purified in concentrations that would actually do some good. But that was the first of the modern antibiotics, and so those sorts of things really have helped us live longer. So World War II, where soldiers were getting battlefield wounds and infections and really needing some antibiotics, certainly thrust the antibiotics research into the forefront. And it's hard when you look at what's going on in other parts of the world to not help people if you have things that can be life-saving treatments. And given all of the media coverage, and now given TVs, everybody can see what's available. And if we withhold it, we're viewed as being unethical. But if we give it to cultures where Social Security was having a lot of kids so somebody would survive to adulthood and be able to take care of you in your old age, that has led to certain areas of the globe having these population booms. But they've looked and they found out that education of young girls and getting them into the workforce, into professional positions, usually helps tail off that birth rate. So that's why I always support UNICEF and look for those programs that help educate women in third world countries, because I think that's a good way to counteract that. And as much as I'd like to say the scientific method is how discoveries are made, well, a lot of times they're done accidentally. So, and sometimes they're done when an experiment fails. For instance, Einstein's theory of relativity came about when somebody tried to measure the speed of light, and the experiment fails. And what Einstein came to appreciate was that as you approach the speed of light, time slows down, distances shrink. These were unexpected consequences from our current understandings, and it was that failure that led to that development. And then, as I said, Fleming discovered penicillin accidentally. What did he do? He left his petri dishes with his bacterial cultures uncovered and left them open to contamination. And somebody working one floor down was working with bread mold stuff, and the mold spores found their way from one floor down into his petri dishes. He was going to throw them away because he said, uh-oh, I got mold on these. And then he said, there's an area around the edge of the mold where the bacteria aren't growing, and that was the aha insight moment. So a lot of times it's not a planned hypothesis that you're testing that leads to development. Luckily, I'm not worried about being unemployed because a lot of science is still out of reach. A lot of processes are very, very complicated, and we just seem doomed to never quite understand them, although we'll keep trying. So, for instance, as a PhD chemist, I can't tell you how electrons move around the nucleus of an atom. That old notion of them orbiting like planets, that doesn't work. There's physics problems with that. But every time we go in and look at an electron, we alter what it's doing. It's like driving along in a Mack truck and hitting a mosquito with the windshield and saying, oh, there was a mosquito right there. But you're not going to know what the mosquito is going to do next because you're carrying it down the road as a splat on your windshield. When we touch an electron, we splat it against the windshield. We know where they spend time, but we don't know how they get from one point to another, or if that's even the right question to ask, because in some instances they act like waves rather than particles. And boy, this is one that gives me trouble. People say, how does gravity work? Or how does a magnet work? What's actually doing the tugging? I don't know. I'm glad it works, though. Just think what would happen if Congress outlawed gravity. There's a bottomless abyss that starts at the top of our hair without gravity, right? So I can't tell you what that tug is. I've heard some hand-waving tries to explain it, but we're really working with a house of cards because fundamentally we don't know how these natural glues work. There's a strong nuclear force, there's electrostatics, there's gravity, and there's the weak nuclear force. Those are the glues that hold the universe together. And I can't tell you how any of them work. So there you go. And another one that I love thinking about is just how complicated it is to make snowflakes and trying to figure out what they're going to look like. So it turns out that it's very difficult to know what happens, but we certainly see snowflakes grow all the time. If you want to treat yourself, just type snowcrystals.com into your web browser, and you can learn how people try to figure out what goes on in snowflakes. Sometimes the faces grow, sometimes the edges grow, sometimes the points grow, and luckily the size of snowflakes is small enough that probably the whole snowflake is in the same conditions within the size of the snowflake, so all 6 points grow at the same time. But there are movies on this site where you can actually watch snowflakes grow under artificial conditions. But just look at some of these stunners. I just find them fascinating. In fact, I had trouble because as I was driving home tonight, it was snowing. I was trying to see on the windshield of my car what kind of snowflakes were we getting. So I mean, this is just fascinating to me. Look at the symmetry that they achieve. And there are thousands and thousands and thousands of them that melt on my hand every time I go out cross-country skiing and it's snowing. How about this one? These are called capped rods. I saw these in Glacier Park on my parka last January on Martin Luther King Day. I was skiing. By golly, there they are. It was kind of a cold day, and for the first time I saw that shape of snowflake. So anyway, these are things that we're way far away from understanding. So there's plenty to keep us busy. We can duplicate a little bit of the website. We can grow a chunk of ice. It won't be a snowflake exactly, but I brought a freezing solution here. So what I'm going to do is I'm going to freeze this solution. We'll ask Steve Running, one of our speakers here who's coming next week, what sort of temperature is that at?
About 22 degrees C.
22 degrees C. We get gender equity here. Not very cold? Room temperature? We'll get another pair of observations. Feels a little cooler than room temperature to me. Right. Although it's usually about 22 degrees C. Real good guess, see? Now if I freeze this, what would you expect it to be? Cold, right? You might be surprised. Let's see if I can freeze it with a magic spell. Oh. I'm going to do a spell. Medulla oblongata, et echinodermata, chiliana cheese enchilada, help gee whiz freeze this water. Oh, I can see the ice crystals forming already. I hold it up here for about 10 seconds. Jack Frost is going to paint frost fingers up the side of the flask. It's frozen solid. See, we made a chunk of ice, and how about the temperature? It's hot. When you put water in the freezer to make ice cubes, what do you have to do to the water in the ice cube tray? You have to take heat away. Yeah, so when the water freezes, it gives off heat. And it's the CFCs and the coolant coils that take it out the back or the bottom of the refrigerator. That's why your cat likes to sleep at the bottom of the refrigerator, because all that heat is coming right out there from making the ice. So I'll pass that around and you can look. So what's going on here? Well, I know a little bit about freezing. So what I have was a supersaturated solution of sodium acetate. I took a whole pile of this long formula. This is what you'd have left over if you mixed baking soda and vinegar and let the CO2 bubble off and then let the water evaporate also. You can take a whole pile of it, a few tablespoons of hot water, put it on the hot plate, put the heat in so it will dissolve, and then cool it off carefully. And then there's a seed crystal that's going to put a template, a pattern in there for it to follow. Where did the seed crystal come? Right here. I stuck my middle finger in there when I picked up the flask, and when I snapped my finger, I just dislodged a seed crystal or two. I've got enough to do about 30 flasks right there, so I'll save them for the next time. And if one of those seed crystals gets in there, and I'm pretty good aim right now, there's the incantation. It sets up a template, and over a few seconds, the whole thing freezes solid. Now these are actual sequences that I use in my course, so I'm not going to stop to let you take notes. Although the whole course is on the website, but it'd be better yet if you came to class, because I do stuff like this every day, just so they'll come to class, right? And this is a sustainable demonstration, and an environmentally friendly one, because all I have to do is put it on the hot plate again, and then I can use it tomorrow for another audience. Just put the cork back on. It sometimes trips by just being splashed up against a crack that has the right geometry, so I always bring two, just in case one of them triggers from vibrations and sloshing around. So, what we're going to do over the next 6 weeks is visit various kinds of science. Ken already told you what the topics are and the various speakers. So we're going to get some global science, earth science from Steve Running. Boy, one of the things that the science fiction writers didn't develop well enough was information technology. They were way out of hand as far as space travel went, and way low on understanding how information technology would expand. So Steve's going to talk about about the power of information technology. And then we have astronomy with the sun. We have the smoke stuff, which we live with here. We have water, and then we have food. And of course, food is like the hydrogen in the hydrogen plus oxygen reaction. That's where we get our energy from. And we breathe oxygen because oxygen will grab those electrons away from the food and release energy in the process. So, what I thought I would talk about today is, as my wife says, the most photogenic research project you've ever been associated with. And that's the Bee Alert project. People sort of cringe when I talk about chemistry, but most people like honeybees, although some people are allergic to honeybee stings, or at least they think they are. If you get stung and you don't have a stinger still sitting in your hand, it wasn't a honeybee that stung you. It's probably a wasp or another kind of bee. But I've been associated with this project since 1992. It's grown and involved lots of people. This isn't the whole team by any means. I've probably worked with a total of 50 different PhD level scientists and a whole host of technicians and students. This is just the group that was sort of in the various roles here at UM when I made this slide a couple years ago. So Jerry Bromenshank from the Division of Biological Sciences is the overall project director. He doesn't have to teach like I do, or I shouldn't put it that way. He doesn't get to teach. People cannot drag me away from my course with wild horses. I love doing it. So he's a full-time researcher. Colin Henderson is out at the College of Technology. He teaches anatomy and physiology, but he's an animal behavior specialist. I'm the lead chemist. Bob Seckham is our computer scientist because we use information technology. And Steve Rice is one of the electrical engineering faculty out at the College of Technology. And we have to have new devices, new toys made, and he designs them for us and helps build them. These are our high-tech beehives. In fact, we call them condos. The little porches sticking out the front are infrared tunnel systems that count every bee that leaves and comes back to the hive. They have to trip an infrared beam in the tunnel, and there's 2 detectors in the floor so we know if they're going out or coming in. What's kind of fun is there's always a couple of sentry bees at the entrance of the hive making sure that foreigners don't get in. And overnight, you can see them sitting in the tunnel right under the infrared emitting diode for our counter because it's a heat lamp for them. So they want to have a heated guard shack. So what have we been doing with these bees? Well, we've had different stages, and we sort of visualized it like this at the beginning. We thought first we would do what's called passive monitoring, where we just put beehives down in an area, send bees out to do what bees do, and then as a chemist I would look to see what they came in with at the end, what they tracked in on their dirty little bee feet, or what ended up in the air in the beehive. We thought we might try to pull them into an area that we particularly wanted to search by putting a chemical down that they like the smell of. Bees find their food by smell, and they'll come check out an area if it has the right smell. We thought that would be sort of an intermediate way to do things towards actually training them to go out and look for things that the government might be interested in. Turns out we can do the last one so well that we never had to do the middle one too much. We did use it to help bring bees into onion fields so the bees would pollinate the onions, because there was only about a 10-day window for pollinating onions to set seed, and a seed company was really concerned with the death of a lot of the wild bee colonies, that they'd get a sufficient pollination on their crop. So I thought I would show you a little bit of the passive searching. This was mostly done at Aberdeen Proving Ground in Maryland. And for about 6 summers, I spent more time on the East Coast than I wanted to. I'd rather be out here in Montana. But we sent the bees out looking for contaminants on the peninsula where the chemical weapons program for the U.S. government had been located since 1908. And as bees go out, they fly along and build up an electrostatic charge, and they pick up pollen, they pick up grains of soil, they pick up air particulates, and they bring them back to the hive. That's why Jerry likes to call them flying electrostatic dust mops. And when you put a hive down, the bees go out about a half mile in each direction. So boy, this is a sampler where me as a chemist that has a mile-wide nozzle. If you just have a little sniffer sticking up out of a truck, how much of an air sample are you going to get? You put down a bee colony, boy, you get a nice big sample. You can see that we were written up here in Science News. Here's just a blown up picture of what a bee leg looks like. Needs to shave, there's a lot of hair on the leg here. Right? But you can see the round stuff is pollen, and then the little angular granules, those are air particulates and soil flecks. So the bee combs those off the bristles into a bundle, regurgitates a little bit of honey, kneads it into a doughy mass, and sticks it on a spike on the back leg. They always called it a pollen basket, but really it's a spike that it goes on. And we make the bees sometimes go through an obstacle course to get into the hive, and that pollen bundle gets bumped, and it drops through a screen, and then I can see what they came home with, right? But most of them make it in okay. We're really very nice to our bees. We've only gotten one complaint over the years as far as animal rights go with our bees, and that was that we were forcing them to do military service even though they weren't U.S. citizens. But we always use natural-born, U.S.-born honeybees. We've looked at how chemicals move through the hive so that when I sample, I get an idea of where I need to sniff for what chemicals. Dave Jones, who's the high school chemistry teacher at Big Sky, did his MS research with me, and this is one of his devices. Here's what it looks like when we're out in the field doing that passive monitoring. We just put down one of these little mini hives, holds about 15,000 bees, so that's a lot of little samplers going out there. And I just put one of my sniffing tubes into the hive. This is sort of like the filter on a Brita water pitcher. It just absorbs lots of different chemicals, and then I bring it back to the lab over in the chem farm building, bake them off into my instrument, and I can tell exactly what's there. Here's a list of some of the things that we found. You can see I found industrial chemicals, I found tear gas residues, radioactive contamination, fuel residues, explosives, toxic heavy metals. I found more than 500 different kinds of contaminants that the bees can bring back and we can look at. So it's a real quick snapshot of what's out there and getting into the food chain. Here's the upper part of that Edgewood Peninsula. This was our sampling site pattern for 1997. They wanted us to check out the Bush River Peninsula, which is this area. This is where we have most of the remaining stores of chemical weapons in the U.S. They're kept there so that we can develop protective devices for our troops in case another country wants to use them against U.S. soldiers. So they have them there so that they can do that. But they worry about them, and EPA has been in there to sample, so they said, show us what your honeybees can do. He said, well, you've got some radioactive spills over here, right there on the docks. They said, oh, that's Navy. This was an Army base. That's where they come in and they unload stuff and load stuff onto their ships. I said, well, how about the Navy being down here? Because you got Agent CN leaking out of your buildings there. And they said, darn. EPA hadn't found that, but we know some of those canisters sometimes go bad. So the bees have been pretty good. In fact, in one case, we could tell that our honeybees were getting into a hobbyist honeybee set of hives because the pesticide that our host for some of our experimental hives used was showing up in our bee hives, and the only way it could show up there is if our bees were getting into his hives and stealing honey and beeswax from his colonies, because we didn't use that pesticide and he did. We've also looked for explosive residues. This is the kind of work I worked on when I was at Oak Ridge National Labs. In fact, here you can see Ralph Ilgner, who's one of the fellows that I worked with. Mike Sigmund was the principal research collaborator down there. And you can see that we've got a whole bunch of peaks here, and a couple of them that I'll put signs up right now. You can see nitroglycerin and TNT. So the bees do bring back a signature of explosive residues in the area. How about this active searching? This is really fascinating, and I found it a lot of fun. We were doing the work at Aberdeen Proving Ground and getting stuff out. We got visited by DARPA. That's the Defense Advanced Research Projects Agency, and they said, do you think you could train your bees to go looking for things they don't normally forage for, like buried landmines, hidden chemical or biological weapons, clandestine drug labs? And we said, well, we have some ideas of how we could test that out. And they said, okay, show us. So we went to the literature and studied explosives first. And it turns out the most widely used explosive for military applications is TNT. Its full name is 2,4,6-trinitrotoluene. A hexagon of 6 carbon atoms that I've numbered 1 through 6, with one sticking out, another one sticking out the top, is called toluene. And if you have 3 nitro groups, NO2 groups, that makes up trinitrotoluene. This can be molded almost like plastic parts and used in trigger devices for landmines and other things. So even though the main charge may not be TNT, they use it in a lot of the triggering devices. And luckily for us, it lands in the smell receptor just like a lot of aroma ingredients do for flowers. So if you stick your nose in a bottle of TNT, it smells like perfume. It actually smells like the cosmetics counter at the store where my mom used to buy dresses. Hahn's Dress Shop in Boulder. That's what it smells like to me. And it must smell good to the bees too. We don't actually use TNT. We use a real similar product. See the difference? At position 6. It's missing a nitro group. This one is a little bit lighter, so it gets into the air easier. It's a little less sticky as far as sticking to the soil goes. So if you sniff above a landmine, this is the thing that's present in highest concentration. And we were interested in getting the dollars from the politics of this project, so we wanted to start with something that we had the best chance of success for. Why try for something real hard first time, right? So we thought we would use this as our first explosive. But it's also very prevalent, so that's not bad. And what we did was we just conditioned the bees to think they were going to get fed if they followed this smell. So we made a water-sugar solution, 2 parts water to 1 part sugar, at syrup, and we put it around the smell of the dinitrotoluene, so the bees start saying, smells like food, just like the odor of popcorn. The aroma of popcorn says, where is it, where is it? That's what this chemical does for the bees. How do we know that they like it and can smell it? Well, we do this little thing called a proboscis extension response test. So what we do is we put bees in a straitjacket, which is made out of a pipette tip. It's got a little bit of tape so wiggly gals don't get loose. And then we puff the scent of the explosive at the bee. So while the bee is surrounded by that aroma, it's saying, what is that? We have one of our bee wranglers reach forward with a syringe of syrup and feed it a little drop of syrup. And it says, hey, not bad. So we puff the scent, feed the bee, wait about a minute and a half. Puff the scent, feed the bee, wait about a minute and a half. We do that about 6 times, and then we puff the scent, and guess what? No food. And if the bee has learned the smell of food, it sticks its proboscis out, expecting that bee wrangler to reach forward with a drop of syrup. And if it does that, we say, it can smell it, it thinks it's food, we're home free. And this was very satisfying for me to actually learn and use about proboscises, because I did it in Cootie, that game of Cootie, years and years and years trying to get that proboscis. I actually have used proboscises in my professional life now. Now, you don't have to take my word for this. You can actually watch the bees do it, because I brought some little movies tonight. We'll see how this works.
B20, train 3.
So here's the bee in the straitjacket. Now when the slider gets over about here, you'll hear a beep in the soundtrack. That's when we release the scent. And then you'll see the bee wrangler reach forward with the syrup drop on the syringe. Beep, there's the scent. Here comes the drop of syrup. Out comes the proboscis. The tongue is kind of flexible, and it needs that proboscis to feed it down to the bottom of a tubular flower. So the proboscis is actually slide for the flexible tongue. That's how we do the initial training. How does it look like when they've been conditioned and we don't come forward with the nectar? No nectar this time. Again, the beep was about here. I can't hear the beep on this particular soundtrack, so we didn't get the microphone placed to hear the beep. About right there. Up the scent. Smell that? I guess there's a little, see the proboscis come flying out? Listen to what the wrangler said.
No doubt in that one, huh?
Yeah, see, that's a really good one. So if the bee does that, then it means we can train a whole hive all at once. So with no smackerel coming forth, it sticks out its proboscis. So this was our early form of feeders. We just took an Algene bottle and made our syrup in it and turned it upside down on a plastic disc with some grooves scratched in it. Sort of works like one of those poultry watering cans. The syrup oozes out a little bit. The bees lap it up. This is Mall of America for the bees. Normally they have to visit 50 to 200 flower parts to get a full honey crop. One-stop shopping. They like this so well that you can actually stroke them like little pets while they're feeding. They don't pay any attention to you. They say, "This is the biggest flower I have ever found." And they go back to the hive and say, "Look for this one, look for this one." When they come back, they exchange some nectar, and of course they tell everybody where it is. But there are so many bees looking that they go looking everywhere at once. We didn't appreciate that so much at first. The bees can empty a quart bottle like this in 40 minutes. And if you calculate how much a bee can carry, that's 25,000 bee visits. So I mean, they just go wild over this. And it saves them a lot of energy. Bees wear themselves out by flying. So if they can fill up in one stop, we actually have bees that are living longer because they're working with us. See, so those animal rights people have nothing to worry about. They're very nice to our bees. Of course, if you get money from the government, we actually got contracts, not grants, where we had deliverables by certain dates. You have to show them that this works. And we were part of 40 projects that were originally funded to try different animal-y sorts of things. And they built this big tent down in San Antonio, Texas. And we had to take our equipment down there and show them that the bees could find the goodies. So this is a big tent. It's an acre in footprint and 40 feet tall. It's made out of that mesh fabric that the ventilation panels on sports caps are made out of. The only trouble with it is every time a thunderstorm came through San Antonio, it would rip apart and they'd have to fix it before we could do more runs. Eventually what we did, took them about a year to get it all working. Eventually what we did is we took our equipment down there, we got local bees. We didn't take trained bees down there because it doesn't take very long to train a bee. You could see 20 minutes was our training cycle. We just got local bees and put out feeders. These are now fancy computer valve controlled feeders, and let the bees feed at those plates for 2 days with the smell of DNT. And then each day the testing officials would take a hive and wheel it inside the tent. You can't come in. They were afraid we would put down attractive chemicals and draw the bees over there. And there were signs that said which target had the real stuff in it. They take them inside and put the beehive on one of 3 locations. They had 3 video cameras set up. At one location they put some sand-filled petri dishes with a little bit of explosive mixed in with the sand. Another place was just the petri dishes with sand. Another one was just a camera by itself. And then they would see what the bees did. Here's a picture inside the tent. You can see the video camera. Sort of looks like a big calla lily. And since bees use visual cues too to find food, we thought we better have that camera by itself just to see if bees were looking for a white thing sticking up. How did they do? Our officer who was doing the test thought this was a big boondoggle that was costing the government a lot of money. Well, here's how the trials went. The first hive went in. The bees that were seen in the counting period at the hot plate were 80, and at the other 2 cameras added together were 2. They took in a different colony the next day, 107 to 0. They were our all-stars. 3rd colony, 4th colony, 5th, 6th. After 6 days in a row, the officer in charge of the testing, who was a radar officer, said, "Well, I'm going to have to eat some crow because your bees are better at finding the explosives than my radar is at finding airplanes. We got an awful lot of false hits." So he said, "I'm not going to kill any more bees." based on the results of this test, our project officer felt optimistic enough that he sent an article to the New York Times, and it showed up, the contents of that article showed up on Jay Leno a couple of nights later. It said, "Did you see what the Pentagon is doing?" Didn't say University of Montana, but there's a lot of people working on this, so that's okay. They're training bees to find bombs. I can just see it the next time I go to the airport. I'm gonna have to take off my shoes, undo my belt buckle, and then they're gonna throw a bunch of honeybees at me. So I think I've really matured as a scientist when my research project shows up in Jay Leno's mono, right? It's also showed up in National Enquirer and The Sun, some of those tabloids. I didn't put those into my advancement documentation. We actually went to see what levels the bees were detecting in the air. Now, dogs can sniff things really at low levels, but they suspect that they might get little bits of soil in their muzzle and be getting more concentrated samples of the explosives than just in the air. Our bees are flying in the air. So we stuck a little sniffing pump a foot downwind and 6 inches above the soil and sniffed to see what was there. 74 parts per trillion, that close to the target. If you calculate how that gets diluted out and dispersed as you move away, by the time you're 10 feet out, you're down to 1.5 parts per trillion. We see bees 100 feet out from our targets, making a right turn and coming up the scent plume into our samples. So they're down in the parts per quadrillion range. You got to remember that bees smell their food. That's how they survive. So it's a very keenly developed sense of smell. The sense of smell receptors are out on their antennae. And they have 7 different kinds. Humans only have 4. So they can smell a much broader range of materials too. So how might you see where these bees are going? Well, first thing we thought was we'll put little electronic tags on the bees. This is a lot of work. This kind was too heavy. This weighed 27 milligrams, and a full load for a bee is 50. The bee was fine going out to our feeder, but coming back it had to jettison some fuel to keep flying. So we've gotten to different techniques now. So working with the explosive specialists down at Sandia National Lab, who also happen to be beekeepers, they thought about using LIDAR. LIDAR is used to look at air pollution. So what you do is you take a pulsed laser beam and send it out across the ground. When it hits the bee, it gets backscattered. You set up a telescope and a detector and look for a green flash, and there's a bee. Does this work? Well, here's the first test. We had to put the laser far enough back from the beehive that it wouldn't fry the bee if it hit it in the air. And you can see that we had a beehive and a feeder. The panel to the right shows where the LIDAR system was. At 1,300 meters out, that's almost a mile, we could see individual bees. So this looks like a pretty nifty technique. So we've been working with the laser people over at Bozeman. We don't have the right kind of laser expertise here, so we're trying to keep this a Made in Montana project. So Joe Shaw and some people from NOAA got a LIDAR unit together, and we went down to Fort Leonard Wood to see if the bees flying out over a minefield could locate where the landmines were. So I'll show you another little video clip now. Well, maybe I'll show a few more slides here, then it'll make more sense. Here's what the situation looked like. We had the LIDAR unit set back a little bit from the minefield, and we sent out a beam of green light and swept it back and forth across the minefield, sort of like the spotlight at a prison, right? Except we're just watching the bees and then piling up those images. So let's see what that looks like.
It's basic Pavlovian conditioning, the same way
So here's
you train
Jerry.
a dog or a porpoise or a seal or a whale. Same type of operating conditioning or training that is used for these other organisms applies to
Hopefully
bees
that full
also.
screen will disappear.
And the one reward that drives them is served. Free food.
This whole system is set up to do is to mimic some sort of weird flower. What we've got is an air pressure tank that maintains pressure on the
Try it again here.
syrup canister. On the time signal, the valve opens.
It's Colin
and
Henderson
distributes syrup
speaking now.
through this network of tubing to each of the feeder plates. We have those
Cameron
feeder
really
plates
got into
metered
following
down
that too.
so that there's a flow that takes
And you
approximately
kinda
a
dizzy.
minute to deliver 100 mils of fluid, which is what it takes the bees 15 minutes to drink. What we do is take advantage
Oh,
of bee
there we go.
behavior by tricking them into thinking that here's a flower that has a very
There's one
rich
of our
reward, has a
more
very
up-to-date
pure
feeder
scent,
plates.
and they can land, they can walk around, and if you watch, they're busy probing with their little proboscis, trying to find
That's
the
the
best
proboscis.
nectar, just like they would on a flower. So we've got our flower here, we've got a ring here,
There's a
that's the
mold
scent.
that we put our
Ring,
scents
and in
in.
the center is the nectary. Nectaries tend to be in the center of the flowers. Bees will fly over the fragrance areas and into the nectary. It's just a weird pseudo flower. The scent that we're using for this case, we're trying to find explosives. One of the strongest contaminants and breakdown products of explosives is a component called 2,4-DNT, 2,4-dinitrotoluene. It's not explosive, it's
See,
classified
they
as
can
poison.
smell it in the
but
bottle.
It vaporizes, it bleeds through plastic.
There's the
it
minefield.
disperses through the
The
soil.
white
and
flags
produces
mark
a
out a
vapor
grid
plume above the
that we're
place
gonna
where the
plot bee
explosive is
densities
contained,
against.
that the bees very quickly condition to and associate with the sugar reward. This is our control
There's Colin.
sample. What we've got is a little bit of DNT, and it's going to produce a vapor plume and no reward, and we're going to see if insects, bees, in fact, will come to it.
Takes about 20 seconds for them to find
This
it.
is over.
There's one coming up the scent
Here she
plume.
comes. Oh, she's in a hurry. Following. Here comes one right behind her.
Another incoming.
And
Yeah,
she
see, so-
made it.
Say food.
Accompanied by a friend.
So now here's the LiDAR tracking.
We're trying to get some sort of a spatial map of where bees are going as they flush off
A
these
green laser
plates.
beam.
We've known for a long time that bees find our plates, find
They're
targets when
sweeping
they're out
back
there. We
and
don't know
forth.
how they get there. And this LiDAR is
About
able to
14
visualize
seconds
what we
to
think are
sweep
individual
across the
bees. So
field.
we're going to have them scan the airspace.
And see the
like
feeder
minefields
plates
today,
and the
and
field
see if we can
behind.
get an idea of where the masses of bees are going after they leave these plates.
So we're gonna scan the laser beam side to side
There's
in
Joe
the
Shaw,
minefield behind me here.
Physics faculty
And
from
we'll
Bozeman.
concentrate particularly on the front row.
He made sure he
In
wore
that
his
calibration
Montana
row,
State
we know
shirt
the
with
location
the camera.
of each line.
Just as Colin was wearing his College of Technology shirt.
So we're going to be looking back and forth with the idea being that we're looking for peaks of bee density, basically any kind of bee clustering over time. This is the computer that collects the data, rack full of electronics. This is the optical package with the detector at the back end, associated electronics.
There's the telescope.
Telescope here where the light gets collected. The laser head is on the bottom up there and it shoots out into the field that you're looking at.
These guys are setting up the laser. As soon as it's ready to go,
Detectors sticking out
we
going around.
what we want to do for the scanning program. They're ready to roll as soon as our laser's up and tuned.
Hello guys, we're gonna fire up the laser.
Okay.
See it starting to sweep across the field.
Okay, on this scan, which shows a single shot, you'll be able to see the bees. We're looking for bees inside of the minefield. The cursor right now is at the front of the minefield. This is all the minefield through here. And here's where the back is approximately. And a bee would show up on this scan as a very brief spike. There was one. Another bee here. That was a big bright one. There was a big one right in here. There was another one.
So that gives you an idea of how that part works. How did they do? Well, here's what the data looks like coming back from the LiDAR. The big red peaks, those are the camera stands and other posts sticking out of the ground. The little blips that are labeled B, that's a single bee sending back some laser light, and you just stack them up over time. Here's what the map of the minefield looked like underneath the white grid of flags according to the Sandia chemists. They sampled the soil, they sampled the air, and built contour lines showing the strength of the chemical emissions. Now, it turns out that this big one right in the center, that was actually a surface spill that got cleaned up from a previous group. And this was taken about 2 weeks before we got there. Here's how the bees did from the video cameras. Not bad. If you look, we didn't particularly pick up that source. And again, I don't know how strong the wind variation was there, but it was good enough that the test facility people said, "Did you guys cheat?" Because I mean, it's kind of spooky, and they said, "This is unreal to get contours like that." We said, "No." How did the LiDAR do? Here's the LiDAR map. I don't think it's quite as good as the video camera map, but this was the very first run on the LiDAR. And Joe is working at trying to look at the polarization of the light and the wing beat frequency and fine tune it. And he's coming back this summer for some more tests. But he saved our bacon as far as did we cheat or not, because the LiDAR was looking beyond just the field where the landmines were located, and he said, "What's over at this mark, this X here?" The bees were hanging out there, and he said, "The bees don't buzz around an area just for no reason. They must have smelled food there." They took a soil sample and analyzed it, and they said, "Oh my gosh, we didn't even know there was anything over there. So your bees found something that we didn't know about. We believe you now." So we're real anxious to deploy this to actually look for landmines. It's just that we're being funded by the Department of Defense, and humanitarian demining isn't high on their agendas. So we're trying to work with the State Department and the U.S. Agency for International Development to see if we can do that. What's the U.S. government more concerned with? Homeland Security. So actually, I wasn't there the day they filmed the stuff on the minefield, because I was talking at a Homeland Security conference, which is our main funding source right now. And how would you use these for Homeland Security? Well, similar to the way Jay Leno talked about. So I'll show you one more little film. So you may not have known this, but there is a security checkpoint out on the road to the Historical Museum at Fort Missoula. Or at least we set up a simulated one. So here was a trailer park, or a place where a trailer being towed by a truck had to stop for 45 seconds. The driver was asked a series of questions. Didn't matter what his answers were. We were trying to get the truck to sit there for 45 minutes and check out the box. This is an empty box. We did get a wasp that checked this one out. I don't know why, but probably saw it go into the box there. And after 45 seconds here, no obvious activity around the box. So the person looking at the monitors would say, this one looks clean. It's free to go. Why don't you pull it on out of here? So 45 seconds is being long. There we go. Okay. Now we're going to switch out the tub. Same trailer, same vehicle, but now the tub has a box with explosives in it. The jars are sealed, but you saw the bees come up to that sealed jar of explosive. Watch after about 20 seconds here. See the bees starting to accumulate there? They say, "I smell food in that box." So the person monitoring the screen says, "Oh, we better have this one pull into the inspection bay." Now we do have it video enhanced here. This is a black and white version of the test. And now anything that's a bunch of pixels about the size of a bee moving around gets a red box. Here's the empty box. It should be ready to pull out in just a second here. And now we'll look at the hot one. And you'll see the little red boxes coming with the bees. And after about 20 seconds here, of course, if the computer can draw the little boxes, it can run a count up on the screen too and say, here's a suspicious vehicle. So we've been testing this all over the place, down in Florida along the coast, down in Arizona by Yuma along the border. So we're hoping to use the bees to do some homeland security work for us too. So, I think I'm about at the end of my time. Can science save the world? I could have told you this at the beginning. No, science is impartial, right? Doesn't care whether the world survives or not. It's people that are going to have to save the world. So it's got to be more than just scientists. But science can certainly provide some dandy tools and some good insights as to how to go about this. I thought this was a good quote to end with. The way biotechnology is going, we're going to know how to make a pretty good likeness of a human before long, and we still won't know how to define what a good human is. So the hard sciences are probably further along than the soft sciences. So we need soft sciences too. And of course, the humanities, there's something about a good book that can stir up the emotions much more than reading a scientific article, I guarantee you. So we need all sorts of talent. So anyway, thank you for your attention, and I'd be happy to answer any questions if you have them. Remember to use the microphone. I just feel so lucky to be involved with fun stuff like this, and I can't wait to come to work each day to figure out what we're going to try next.
Garrett. Am I talking? Oh, there it is. Okay. I see the bees keep coming back to this smell, but after a while, when they don't find any sugar, are they going to keep coming back, or how do you keep reprogramming so they're still interested in this smell when they don't get any sugar?
Very good question. And the way we first did our test was we stole the feeder, and they would go for about 20 to 30 minutes. If they don't find any nectar, their gas tank is empty because they're burning honey out there while they're flying around, and if they don't find nectar in the flower, oop, I better head back to the hive. I'm going to be on empty, and then I'm up a creek. So if they don't find a food reward within 30 minutes, they go back to the hive. So our computer-controlled feeders squirt out a little syrup every 15 to 20 minutes. So that feeder plate keeps feeding some of the bees. It's not enough that they can all get fed there, but it's enough to keep them flying, so we can keep them out for a 3-hour period by dosing that plate about every 15 minutes. If you heard the narration from Colin talking about the feeder, talked about the flow rate, he said it delivers 100 mils of syrup, which is what it takes the bees about 15 minutes to eat. That's what we're doing with that.
The thought occurred to me that if our enemy knows that you have such a system, what's to prevent them from countering it by dosing their tanks of the explosives in it with an insecticide?
Yeah, there are countermeasures certainly that you can use against this, and you could put other attractants to draw them to another part of the vehicle. So it's true you could come up with countermeasures. But the bees are still pretty good. Dogs would have the same trouble. You can put things that cause problems for the dog. Our bees don't fly at night. They don't fly when the air temperature is colder than 40 degrees, so there are some limitations. I think it's maybe more useful in a demining situation, maybe than as a security checkpoint.
How do you deal with the average longevity of a bee?
So the bees don't take very long to train. They train in a half a day. A typical forager bee lasts about 2 weeks in the summer. They fly themselves to death. When you're looking at the foraging honeybees, those are the senior citizens of the hive. It takes 3 weeks from egg to emerged adult, 3 weeks working in the hive as a queen bee assistant or a nurse bee, and the foraging is the last stage of their life. So as long as we're constantly running those plates, a new set of bees is constantly being trained to that scent. We can take the feeder plates away for a week to 10 days and bring them out again, and they remember it. So they come back to it much faster than if we were training from scratch. But beyond 2 weeks, we would have to deal with a whole new crop of bees because they don't live much longer than that. Although the bees that go in the winter into the cold season live all winter long in the hive because they don't have to fly, so they don't wear themselves out. So if you want to be a long-lived bee, get born late in the summer. Yes?
This particular odor from the TNT, are there other chemicals in landmines that are explosive that do not have this chemical in them that you'd have to almost retrain the bee or train bees to seek out a whole different odor?
Yeah, we've tried other things to train them too. We've done nitroglycerin, which is found in ammunition. We trained them out at the sheriff's bomb disposal area by the airport a couple summers ago. The same day we were working with nitroglycerin with the honeybees, some FBI agents were doing pistol range qualifying 2 ravines over, and when we came in for lunch, the FBI officer said, "Wow, have you seen how many bees there are today?" I said, "No, are there a lot of bees?" It turns out we were worried about RDX. That's the main explosive that's used in the modern plastic explosives. It stands for Royal Danish or Royal Duke's explosive. It's real sticky, it's real heavy, it doesn't loft into the air. The bees weren't responding to it. But to make it moldable, they mix a little bit of fuel oil and plasticizers in with it, and the bees love the smell of the plasticizers. They can smell C4 in the wrappers, inside the trunk of a car, and find it in 20 seconds. So we're lucky that they mix other stuff in. We've studied cars to see where stuff comes out of them as air heats up inside, and that's where we look for bees hanging out, because we know if the smell is coming out, that's where they'll be flying. Yes?
Do you have any competition in the mechanical, electrical fields where they're trying to replace the bees or something?
We always have to worry about the competition. There is an artificial nose project called Fido, and we've had to compete down in Texas with the Fido detector. The Fido detector suffers from the mile-wide nozzle versus a single point source sampling shortfall. So it takes us about 20 minutes to 2 hours to look at a football field-sized area with our bees. It took the Fido 2 days to crawl over that football field, and they actually had to drive it up to the source of the landmine and have it sit there before it detected a hit. So we thought we did pretty well against the artificial nose. We have to compete against the dogs too, but our bees are good at finding explosives that are being hidden high on a vehicle. The dogs walk around the base. The dogs also require a handler and a lot more than a half a day to train. But we always have to worry about the competition, because with that contract, that's what they're asking us to do.
Whatever made you even think to try this?
Well, Jerry has been a lifelong researcher with bees. He's used bees to sample pollutants all over the place. And when you read the bee literature, biologists who are just studying bee behavior have used things like the smell of anise to draw bees in to target feeders. So we just thought, well, we'll try those techniques with unconventional attractants. And we use that proboscis extension response to survey hundreds and hundreds of different chemicals to see what they could go for. It is totally one of those serendipitous things that TNT smells like food to the bees, or the plasticizer smells like food to the bees. So that's real fortuitous that the molecules that are found in those objects are things that the bees can smell and they don't mind. We've tried to find meth labs, and we're going to play with that a little bit more this summer. Meth labs, in many instances, give off a substance called phenyl-2-propanone that the bees can smell, but it's a repellent. And we don't know if we can condition them against a repellent, so we might have to look for some other odors too. And we're hoping that the P2P doesn't drive them off. But they can smell it. Now, I know people eat Limburger cheese, and I don't like the smell of that, so maybe if the food is good enough, we can get them past P2P.
You know, there's a lot of talk now about science education in the United States and us losing the edge in the sciences. As someone in your position, what would you do to either keep up or increase science education?
So I'm very keenly aware of that, and that's why I go out on the road every May. Ken misread that. I don't talk to grad students, I talk to grade school students. So I like to go out as a wizard and work with the kids in the grade schools to get them excited about science. We're also working to involve high schools and even grade schools in research projects that we're doing here. We have an air sampling network. Dave Jones, who worked in my lab for his master's degree and is now teaching out at Big Sky, he liked the research so well getting his master's degree. He said, I'd like to keep working with you. So now we are sending out air sampling pumps all over western Montana, and high school students are taking them home, looking at the air in their houses and the air in their yards, sending that information back to us. They're sending the samples to us and we analyze them. They're catching particulates. We're looking at them on the electron microscope that they can watch actually over the internet. So we're trying to draw them into a whole western Montana research network. So we think if we can get the kids participating in real research and finding out things before the experts know what the answers are, I think they'll maybe get a little bit stronger dose of science and maybe want to stick with it. So we're trying to reach out and make them part of our enterprise.
I'm curious about the process in the bees making honey and whether or not the honey, how it is purified, or the honey we're eating have some of the impurities that they're bringing back to the hive.
That's a good question. They do bring back contaminants to the hive. Some of it ends up in the honeycomb, some of it ends up in the honey. It's usually at pretty low levels. As far as how good the honey is from the standpoint of cleanliness, if you think about it, the honeybees put it into their honey crop and then they regurgitate it. But it turns out that honey naturally has hydrogen peroxide in it, which is an antibiotic, and it's why they used to dress wounds with honey in the past, because that hydrogen peroxide kills the microbes. As far as the contaminants go, most of them end up in the honeycomb, so as long as you eat the honey by itself, that's less problematic than a lot of honeycomb. But good question.
With your grade school science curriculum, is there any way that you can make the curriculum smell like cheese pizza?
Oh, I could sniff a cheese pizza with my equipment, and we could go for that. You know, that's how they make those flavorings for chips. If you want to have a pizza or a pepperoni flavored chip, they sniff with chemical sampling equipment, look to see what's there, and then they mix those chemicals together and put it on the chips. That's industrial espionage that you can do that. Maybe I'll take one more question. It's holding a lot of people here for questions, but I'd be happy to stick around and answer them one-on-one if you'd like me to.
Are any of the odors toxic to the birds? I mean, to the bees?
Are any of the odors?
That used to go in the mines, you know, they would put birds in mines and canaries.
Right. Now many of the things that the bees have been exposed to are toxic in much higher levels. The bees are smelling them at parts per trillion levels typically, which is a sub-toxic level for the bees. They don't live very long, so they don't build things up like higher organisms do over a lifespan. So the bees aren't being hammered as much. Now, we did run into one location at Aberdeen Proving Ground that was toxic to the bees. We found a queen crawling on the ground outside the beehives, and that's not what they do. They fly once outside the hive for mating and then go in and lay eggs for the rest of their lives. And I came up to one of my air samplers, and there was a queen crawling on the ground. We put paint spots on them so that when the bee wranglers work in the hive, they don't smash them accidentally, because the colony doesn't work without the queen. I thought, that's strange. So we had our bee wranglers check out all of the hives in that particular sampling cluster, and it turned out that 5 out of the 7 hives were without queens. And when I looked at my sniffing data, they were getting a complex mixture of industrial chemicals. And we reported this to the officials at Aberdeen Proving Ground, and they said, Well, those are in the water, as we've seen them. The U.S. Geological Survey has sampled the water, but that's 168 feet down. And I said, what's in that big nylon tank out by that site? They said, oh, well, when the USGS comes to sample the wells, they have to remove 3 well volumes of water and let fresh stuff come in. Bill Wisner's back there shaking his head, right? Have to get a fresh water sample, and they dump them in that tank. And I said, well, there's how the stuff comes 168 feet up to the surface and is available for the bees to get into. Bees like water to make bee bread and royal jelly, and they spread it on the comb and wave their wings over it to cool off the hive when it gets too hot. By putting that tank there, they're poisoning the bees. So that's the only instance where our bees have really been hammered by anything toxic. And we can see that in the bee counts.
Well, thanks so much, Garen Smith. Thank you for coming out.